subleading, come si dice, cioè se funziona bene è conveniente.
Meglio così non rimane traccia di quello che viene detto.
Subleading se l'ha sentito sicuramente.
So welcome back. We're going to start this session of 3 talks with Monica Verducci, who is going to talk about the challenging searches at the LHC.
Okay, so good morning. So I will talk about these challenging searches. In principle, I will try to highlight the results coming from round 2, and I will try even to give a look at possible perspective from the point of view of ILUMI LHC. So a brief introduction, challenging. So I was wondering which kind of results I could put in this talk. So I decided to point the attention to what is called long-lived searches, so long-lived particles. So this is just because I'm honestly quite familiar with these signatures, and on the other hand, because I think they are quite interesting and even at that point challenging from the point of view of the analysis strategy, and so the approaching from the detector side. So clearly the long-lived particle can be predicted by different models. Here, just for your knowledge, I try to make a summary. This comes from another talk by my colleague. So in principle, you have different possible signatures, and the different signatures connected with a possible scenario that can be interpreted to set the limits. So why the long-lived particles are quite challenging from the point of view of the experimental analysis, and this means a trigger analysis tool, etc. Because in principle, this can be overlooked or misidentified by the other searches, and in principle, because they need customized object as trigger, as a selection algorithm to be actually analyzed. So just look at what is called searching for long-lived particles, or a sort of ingredients that you need to take in mind once you're starting an unconventional analysis. In principle, you have to take in mind that these signatures, so long-lived particle, can be very different. So it can depend mostly where the particle, the long-lived particle decays. So in principle, you can look at different observables to identify these long-lived particles. And in particular, this kind of signatures can need standard, non-standard trigger, so mostly customized trigger to identify these objects. And even from the point of view of the reconstruction, they need self-made object. This means that a standard reconstruction, standard trigger, sometimes remove completely these signals. So most of the analyses need to in some case, customize, redone the different algorithm selection, relax cuts or remove cuts to have the signal actually obtained in the data. And even from the point of view of the Monte Carlo, we needed to make custom Monte Carlo, and even for the background rejection, we have non-standard background most in all the cases. Non-standard means that we need even to figure out and to face problem from machine background or cosmic ray muons. So look at the, let's say, the outline of this talk. So I will try to highlight the run to results. Here I have to, I did a sort of choice of the different analyses that I can report for 30 minutes. So I decided to point the attention to disappearing track and displaced vertices, displaced jets, and the large D over the X, what is called mostly hadrons searches. Here just a sketch of what is connected with the displaced vertex, the disappearing track, and the kink track. So I think this is quite challenging from the point of view of the tracking system. And then we will see how can be challenged even the displaced jet and the DA over the X. For what concerns the analysis for run 2, I try to make a sort of highlights and flashing the results connected with the 1615 data taking. So mostly just one analysis is as 2.3 femtobarn inverse. All the others will be focused on the complete data taking 1516. And where it's possible, because we don't have any projection, all the projection for each signature, I can try to make a sort of possible future developments looking at ILUMI LHC. So in this case, just to give you an idea of how the results are being obtained, even if most of the results are for performance and not really setting the limits, the ILUMI, as probably you are already familiar, I'm talking about the 3-acto barn inverse, and so moving from 13 to 6 to 14 TV as a center of mass energy. And mostly, the idea is to scaling the number of events, so the events yields with respect to this change of cross-section and the center of mass energy, and have a particular treatment for the systematic uncertainties. Mostly this is something common with CMS Atlas. So taking the detector or rescaling where needed, and for example, from the theory systematics, have the systematics of the connected with the theory. I will go quite faster with this, probably you're already familiar, so the results will be sitting here, so I will report about 15-16 data taking, and the ILUMI, what is called here, it's phase 2, so we don't have any real results for phase 1, except I think LHC, but all the perspective will be for phase 2, where you're expecting to have an high luminosity. This is the planning luminosity, and mostly it's a really strong redesign and change in the detector layout, mostly for all the detectors. So let's just highlight some of the problems. Without going to the details, I just want to remind you that once we move to high instantaneous luminosity, we increase the mu event. This is the number of interaction per crossing. Now we are running with something that is around 36, roughly speaking. With ILUMI, you're expecting to have 200 vertices. So this will clearly challenge problem in the tracking. Will be a challenge even the mitigation of the pile-up. And this clearly will be all the possible ingredients that we have to take into account once we move to ILUMI. So we increase the luminosity, so we can actually push the limits up, but we have even to face problem connected with the machine working and the detector that should actually face this kind of problem. Take in mind that with upgrade, we will increase mostly for all the detector the physics coverage, so we can improve in the physics coverage for mostly all the analysis, even for the long-lived particle. So it's a balance of the, let's say, the push in ILUMI and the detector coverage, but even we have to take into account the possible challenging from ILUMI and pile-up. So let's move with the disappearing track. So we are talking about something that we have a track, and at some point the track disappears. So we will see which kind of models can actually be used to interpret the results in this case. So for most of the analysis, I try to flash one analysis in Atlas and the other in CMS, and where it's possible, introduce even LSCB results. In this case, I will start with Atlas. Mostly these analyses can be interpreted in the long-lived Chargino in MS model. We have two different actually production mode introduced in this paper, so the electroweak and the strong production. In all the topologies, you can see we have mostly an high jet, so high transverse momentum, large missing transverse energy, and different, depending on the final topology, high jet PT. But the most challenging point is not really the jet or the MET, but really it's what happens to the track originated by the Chargino that decays into neutralino, taking into account that the pion is so soft that cannot be reconstructed. So here the challenge it's the follow. The standard track normally asks for different hits, this is Atlas, in different subsystem of the tracking system. So in this case, since we are looking at a short track, what we call, and we will see labeled as tracklet, we need only pixel hits. So for this reason, the standard track doesn't work. We need to ad hoc rerunning the tracking. In Atlas, this is done in the follow way. So you run the reconstruction, then you run a second reconstruction tracking, where you remove completely the hits already used by the standard track, and you look at the hits that you removed by the previous. Mostly hits, in this case, that actually track, and hits belonging to track that have all the hits along the tracking system. And you just look at hits into the pixel, requesting at least 4 hits in the pixel. So here you can see mostly what happens if you run standard track. This is green, I hope that you can see, but mostly it's clear that this is the pixel, few 10 centimeters from the beam pipe, then you have the SCT, the silicon tracker, and then you have the TRT. So for standard tracker, the regime is that you have a high efficiency once you move to have hits mostly in all the section. For the chargino in this case, so 0.2 nanoseconds, the tau of this particle, you see that if you run this additional tracking, so this alternative, let me call a tracking, you can gain where actually running standard tracking you don't have any signal. So mostly this is the challenge point for this kind of disappearing track. And all the backgrounds, mostly it's classify and actually identify using PT templates for the fit. So you fit the PT of the tracklet. Tracklet means really a segment of track just on the pixel. So this is the results. I will try for all the analysis mostly to point the accent on the strategy and very less on the results. This mostly it's the final results for Atlas, strong with in green the electroweak limits, and this is the electroweak. So here you can see what happens at the ATV, and this is what we have now in 30 TV. So as you can see for let's say shorter lifetime, Atlas improve with respect to ATV. This is mostly because we have an IBL, so we're inserting a tracker in a lower, close to the beam pipe, and then just because even we improve this tracklet reconstruction with 13 TV. We lost a little bit in, let's say, C-tau, but this is mostly because in the previous analysis they use even hits on the SCT, so they actually need a larger, so they are mostly more interesting to larger taus, and now we are focused on shorter taus. This is mostly even for the detector and the readability of the pixel hits in the previous. So this is disappearing track in CMS. I will flash only the results. The analysis is not the same in the sense that they look at track but with missing outer hits, so they really remove track that do not have all in the outer side of the tracking system. They have an ad hoc here trigger. This can improve even the efficiency of the signal. And this mostly it's the plot that show this chargino at different tau, so different lifetime, and that's the number of missing outer hits. So this can explain how the standard objects have mostly no outer hits missing, because you want to have a track with all the hits throughout the tracking system. And this is the number of hits for the signal. So you're expecting a large number of hits missing for this disappearing track. These are the limits. As you can see, for example, in this case, the limits, it's a little bit better in CMS with respect to Atlas. So most probably, I guess that can be from the trigger that is ad hoc in this case, and even the tracking system that it's quite different from the two detectors. So probably in this case, Atlas can be less sensitive. Just a projection for Illumi. This comes from the TDR of the pixel. In this case, this is Atlas. These are the efficiency, the construction efficiency. The dash, it's run 2. The line, it's what we expected with the mu 200, so the study for ITK. ITK, it's the upgrade of the tracking system that will include the coverage of the tracking system. So as you can see here, we are gaining in reconstruction efficiency. This is the charge decay radius. And mostly this is the perspective of the electroweak production that we have seen before, the plot that we have seen before. And this is the expected limits for this perspective for LHC Illumi. So as ITK, yes, ITK it's the new, should increase the coverage up to 4 in ETA. So let's move to the heavy stable charge particles. So in this case, I will report results coming from CMS. So in principle, in this case, you have heavy stable charge particles that are quite massive, that can be defined or identified as stables that actually do not decay into the detector, or metastable that can decay throughout the detector. So the int to identify this particle can be the dA over dx, so the standard Bethe block function, or the long time of flight that this particle can have. So in principle, accessing to the muon detectors to get the time of flight of this particle. In this version of the analysis, CMS use two different approaches. The tracker only, so actually studies the dA over dx, so the ionization of this particle with the function template and then extract the mass. Or the track plus the muon system, so merging the track objects, so the dA over dx information, plus the time of flight coming from the muon system. So even in this case, it's quite relevant, a good reconstruction, so a good fit, a good, actually getting a good really performance in the dA over dx, so the ionization value, and the time of flight, that in this case from CMS, we use only the muon system, so the outer side of the system. These are the mass that you can reconstruct for the signal and the data in the case of different approaches. So this is tracker only, dA over dx, it's used as a benchmark observables to identify long-lived particles, and this is the case where you merge the two. So you combine the two, and these are the limits. In this case, these analyses really span different possibilities for the hadrons, so with the tracker plus the muon spectrometer, and so this is that they set the limits on 7, 8 TV. This was done even in at 7 and 8 TV version. This is the latest version for the 13 TV. The same analysis for Atlas. In this case, we look at the dA over dx only. And so this mostly, it's the function that is fitted from, that template comes from kaons, pions, and protons. Mostly this is the function that look at the most probable value for dA over dx, and depending on beta gamma. So in this case, the analysis look at mostly dA over dx. And this is the limits for the stable and the metastable hadrons. The interpretation is just, in this case, with heavy gluinos. So that's the possible perspective for iLumi. I just report some studies from CMS, so this is the TDR for the iLumi, where they're expecting to improve the time of flight looking at the RPC trigger. And so the RPC trigger, and even looking at different tracking. So this is, for example, the possibility to look at the cluster per track in the inner or outer side of the tracking system. So mostly this is the curve that show the signal track efficiency and the background track efficiency for the iLumi. So mostly this is the different approaches, dA over dx, or dA over dx plus this additional information about the tracking. So I will go to the displaced jets. In this case, we look at displaced jets, means jets that are originating really close to the calorimeter or even inside the calorimeter itself. So they are quite atypical jets. This is the topology. The results are being interpreted inside the hidden sector, so hidden valley, mostly the first model used as a benchmark. So it's a boson decaying a pseudoscala, and this decays in a couple of fermions. And these look like as two jets. These jets are originating this analysis inside the hadronic calorimeter, mostly in the edge between electromagnetic and hadronic calorimeter, so between 2 meters from the beam pipe in Atlas. So these jets are quite atypical, so they are quite narrow in cone because they are originating close to the calorimeter, so they are really with the radius small. With a large energy in the hadronic calorimeter and mostly no energy in the electromagnetic calorimeter. They use these variables, but mostly this is the ratio between the energy. And isolated with respect to the track, because the jet has not a charge track connected. These are the three values, the three observables listed here, ABC. So mostly this is the jet width. As you can see, this is the signal. This is the standard multi-jet. This is the log ratio. So hadronic over electromagnetic energy, this is the standard model, this is the signal. And this is the delta R between jet and tracks. So even in this case, you see that this is the standard model, so close to track, and this is the signals. The signals are at different mass of the boson. The strategy in this case require an ad hoc trigger. This trigger was for this analysis. So the trigger works into the level trigger looking at these properties of the calorimeter and the tracks. And this is completely brand new trigger for this analysis. This is the clear case where the standard trigger actually doesn't work for these long-lived particle signatures. From the point of view of the jet itself, the jets, since they are atypical and they look like as most of the background in Atlas, they need some additional or removing some cuts in the quality of the jets. For example, they have really low EM fraction, so electromagnetic energy, but low EM fraction are removed by the standard quality of the jets. So in this case, they need to, in some case, customize the quality of the jet itself. The final decision and the analysis done running a boost decision tree where mostly the observable fitted in the BDT are what we discussed previously. And so this is the results. As main background, they have multi-jets. This is the blue. And Bib and cosmic ray. Cosmic ray are muons, so from the cosmic ray that can actually mimic that kind of jets. But even a Bib, that is beam-induced background, so mostly beam protons interacting with the collimators that can mimic this kind of jets that travels longitudinally with respect to the beam pipe. And even in this case, the backgrounds are quite atypical. So these are the main problem for this analysis, and all the analysis that actually foreseen displaced jets. This is these are the results for the different mass of this, the boson and the different mass of the pseudoscalar. I think this is quite nice. This is a sort of recasting of the results from CMS, Atlas, and LHC, because they did in some sense the same analysis with the same benchmark models. This is quite old, because this analysis use as a boson an Higgs that decay into a couple of pions, and in this case the branching ratio is 50%. This is use 7 and 8 TeV. As you can see, these are the results from Atlas, these are the results from CMS, and this is what we have from LHC. So clearly this depends even on the model where the decay, the pions decays. So clearly Atlas look at decay into the calorimeter, they look at decay close to the beam pipe, close to the tracker. Yeah, this comes from a recasting from, I think, theorists, looking at results from Atlas and CMS, and then on top there is LHCb. This is done by LCB paper, also community collaboration, but these two plots come from a recasting with a simplified model done by theorists, looking at the acceptance efficiency. This is the possibility for Illumi. I didn't have plots because it's still not published. But in principle, we have some additional study for Illumi because we will improve the segmentation in the calorimeter, so the possibility to identify where the pion decays. So I think this is quite interesting because not only a displaced jet, but you can have even hint on the position of the decay. This is what we discussed previously. So this is LHC results, and this is what they expecting to have for 300 phantom, but this is run 3, so not Illumi, but this is run 3. So I think this is nice to report that even from the LSCB, for this topic, we expecting to have some additional improvement into this phase space for the limits. So quickly on the displaced vertex. In this case, we have vertices displaced, but displaced in the tracker. So that's mostly hadrons use this for air hadrons as models, as referring models for the interpretation and the limits. The selection and the cut require a large MET that use even for the trigger and mostly the selection. The analysis is sensitive to the decays into 30 centimeters, so in the tracker, so in the first part of the tracker. So with respect to the disappearing track, in this case, we run a large radio tracking. So even in this case, the standard track doesn't work. We need to rerun a second tracking that actually look again at the leftover hits, but with the looser cut on D0 and Z0 in this case. So the final selection, as I said, it's MET, cut on MET, and ask at least one good displaced vertex. One point to remark in this case that if the displaced vertex is sitting inside the material veto, so material map, actually inert material around the tracker, these vertices should be removed. And so one of the challenging points, apart from running the large radius tracking from the software point of view, but even identify and have a clear map of the material, because you need to remove the vertices inside the material because can be other interactions that are not really connected with the signal that you are looking for. Displaced vertices in multi-jets events. I just flash in this case as well. So here you have multi-jets as final states. This is for gluino neutralino channel. For the stop, you have dijets. In this case, this is CMS analysis. So they look actually to vertices really close to the beam pipe. So the idea is to have an analysis looking at the distance between the vertices. So here you can see the backgrounds and the different signal, where this is the distance depending on the c-tau of these samples. So mostly this is the analysis for CMS. In this case, this is a middle between displaced vertices, because you look at vertices as a template, but in the final states you have jets. This is the approach for iLumi. In this case, I report Atlas, just because for the tracker we have ITK incline, so mostly the ITK prototype that goes up to for eta in eta, so you can improve clearly here the acceptance for the hits, so you can have an improvement in the reconstruction identification, because you can push far from the 2.5 that is the current limitation. And then the displaced muons. Even in this case, we look at vertices. I will go fast because I think I finished the time. You have vertices in the muon spectrometer. So here you will look at vertices in the muon spectrometer, and then you look at the invariant mass of these dimuons. So this is two dimuons with opposite charge. And in this case, it's challenging because you have to look at vertices in the muon with no track, so muon standalone, that's quite challenging point of view for the perfect tracking. And then you have even two-phase beam, again, induced background, because they can create high PT muons, and cosmic ray, because you have the shower of the muons that travels the muon system. So even in this case, you can have these segments of muon that can mimic mostly the signal. I think this just a flash on the dark photons, because this is the only analysis that I put for LHCb. So this is the dark photon analysis, where you have two muons. This analysis is done with the prompt and displays. This is the display, this is the prompt results. And done in LHCb with the 2016 data. But I like to show this plot that I took from LHCb workshop conference this year, done by Mike, where he put together LHCb results for a dark photon, prompt, let's say displays prompt results, and the CMS and Atlas. It's quite fade, but you can see this is these are the conference and paper results, and these are the displays and prompt lepton jet for the dark photon interpretation. So I think this is a good example of complementarity of the experiment. So finally, I got to the conclusion. So that's mostly the list of the analysis that I report, and I try to make actually a talk mostly focused on the technique and the challenging point of view, challenge point from the reconstruction, identification of these events. Mostly we don't have any discovery clearly, but we really push up the sensitivity in run 2, and there are quite a large number of works already going on for the iLumi to improve, even in this case, the sensitivity, and clearly exploiting the complementarity of the three detectors as well. So I think it's quite good.
Thank you. So we have time for a couple of questions. We had a few already. Yes.
So obviously, how well these searches do at high luminosity depends a lot on the improvements in the detector and the trigger, because a lot of them went by so fast and there were different things that mattered. Could you just say a bit about how firmly these upgrades are set in stone, and sort of maybe a related thing, is the trigger menu going to be, is it very fluid? Is some aspect of it, like, is most of it publishable for use by theorists to see what opportunities there are, or will it be? Thanks.
Okay, so clearly I apologize because I need to go fast for the iLumi. I just flash some results and some of the ingredients. We are proceeding with some publication. So we have already the TDRs that mostly report the possible performance, the upgrades plan, and the performance on the physics, performance on the object, and some results on some perspective on the physics. And we are running on a yellow report, for example, that should collect all of them and make mostly an idea for different topics. I'm just talking about this long-lived particle that is sitting inside the exotics or SUSY's framework. So we have some, I tried to pick up some of the analyses that have, in some case, even some ILUMI. Mostly what I presented is what we have currently, okay? So we don't have much more, even because you need to rerun the limits and you need to decide mostly how you want to scale the events and the systematics. I put in backup mostly some guideline for the yellow report for what concerns the systematics. So you have mostly the idea that we use to put together all these results. But what I presented here from this kind of topics is what we have current. And for long-lived particle, we have only performance, and I think only the disappearing track has some setting limits. Probably, I don't know if I forgot something from CMS for ILUMI addition. I think no.
So if you're interested about trigger and how we're going to do that, then I agree with what you said. Actually, we do not have yet trigger TDRs or trigger menus. And in fact, I think that it's good to have, there is a very big connection with theories to figure out what are the hot signatures that we should make sure that we get. And the system is designed to be more flexible than we have now, of course, to try to catch more things. It's all up there. We're working on it now.
Yeah.
So
On
the next 2 years,
yeah.
there's a lot of work on triggers. Level 1 for CMS will come out in 2 years from now, so that's the moment if you have ideas to talk about.
Yeah, from the point of view of Atlas, we have the trigger, but from this kind of searches, we have only some analysis on level 1 for displaced lepton jets. So improvement, actually the trigger level on muons, because we will change the trigger, so we will need to improve this.
So when you discuss displaced jets, you didn't seem to be using the direction of the jet or finding the vertex. You mainly were using the fact that there was no activity inside some radius and then outside you would find some jets. But Atlas has energy deposition as a function of depth in the calorimeter. Can you actually construct the vertex of a pair of displaced jets?
For this analysis, the answer is not, because this version of the analysis for 13, they're starting to look at the possibility for these displaced jets. I mean, this one. This same analysis that is run on 7 TV, 8 TV, and this is a 13 TV, but only 2015. On 2016, we are actually approving, and they try to look at the sensitivity on the decay position with a multivariate approach. So yes, the answer is we are trying to, but we didn't do in this version of the analysis. So in principle,
I guess I lost the microphone. There are signatures. Okay. I mean, there are signatures with a single displaced jet, where you have a neutral particle that becomes hadronic and it goes off in some direction. And for that, I guess you really need the literal pointing. Yeah,
this is something that we didn't do in Atlas, and I think the analysis is trying to explore in this version of the analysis for 15, 16, and I think in the next step they will try to sampling the calorimeter cells. But this is even technical point because you need the cells informations and from CPU and the size of the objects, it's demanding. But yes, this is something that we are trying to explore.
Okay.
Yeah.
Question actually. So we have this displaced photon analysis.
But that's not
exactly
displaced jets in that way. No.
Exactly. I wanted to just because you quickly mentioned for the displaced vertex, the disappearing track CMS analysis, there is an ad hoc trigger. I didn't understand what you meant with this trigger. So I think Atlas is using missing ET. And you think there's a better trigger?
That's why, because I have some discussion even with the SUSY, let's say, conveners to understand why we are less sensitive. So I try to understand. From this point of view, I understand that with respect to ATV, we lost because the philosophy of the reconstruction was different, so was not so reliable, the pixel. And they needed to add the SCT bits as well, so actually they are more sensitive to the longer lifetime, and they lose in shorter. Something that they improve in the 13 TV, because they are IBL and the most pixel attitude that works better. But with respect to CMS, I try to understand why they are most actually sensitive. So from my understanding, just reading the paper, so I don't know if CMS has some colleagues, the reconstruction works different. So I don't know if this can be neat. And even they mention an ad hoc trigger for these objects. And I don't know if this can be...
By ad hoc, you mean dedicated trigger for this kind
They have some trigger using this PTMIS that works better for these objects. I don't know if this can be the reason why they are stronger or they are more sensitive than Atlas. This is, I'm guessing. I don't know if CMS has... if I didn't find the table with apple to see the efficiency where it dropped, but that's could be...
Okay, I guess it's a story to be continued offline.
Yeah, I don't know.
Okay, thanks a lot, Monica, again.
Thanks.
For this very nice talk. So the usual pointer, you can change the slides. And so the next talk will be by Andrea Vulsa about the energy and accuracy frontier.
This way? The other one? Yes. This way?
Yeah, I think.
It works? Yes. So thank you very much for the invitations. I think that I guess that the mandate that was given by the organizers is to try to convince you that precision physics at the LHC is a topic which is of interest also to BSM persons. I believe that, and I will try to do my best to convince you. So the precision program that, first of all, the LHC has a precision program, and which is in many respects comparable with the one that LEP used to have, and on which our community used to work for very good reasons. And the reason is that at the LHC we can do much more than searching for bumps. And if you just were decoupled from collider physics in the last 20 years, you may find this surprising, and indeed it is surprising. It's due to remarkable progresses that have been made in all these aspects like PDF determination, high-order calculation, precise Monte Carlo generators, and of course brilliant and complicated analysis of which we got a flavor in a couple of two talks ago. Okay, so also, precision is not the bureaucratic certification of the success of the standard model. It is a tool that you used to have. And I think that this misconception is due to the persistent bump hunting mentality that makes that if the LHC was made to discover bumps, it hasn't seen bumps, then there is only the standard model to be seen, and we have to certify that it is really only the standard model that has been seen. But this is not the only possible outcome of this story. So the program develops along two lines, which of course have connections, but it's important to keep them separate. So one is measuring standard model parameters. So that's all what you can do if you assume that there is only the standard model within the reach of the LHC. And we shouldn't forget the LHC has measured one of the standard model input parameters for the first time, and very precisely. This is the Higgs mass. And we also heard about other examples where, rather surprisingly, I would say the LHC can, in principle, well, maybe after the luminosity LHC, reach the frontier, okay, at which we probe these kind of things, okay, comparable with previous experiments. And then there is the other box, which is searching for new physics. And here there are two main items. One is Higgs couplings, that of course you all know is an established success of the LHC. You also know that there are several BSM scenarios, notably composite Higgs, for example, where the constraining power of Higgs coupling determination is comparable or even superior to the one of direct searches, which is showing that actually it may have very well been that already from round one Higgs couplings we may have discovered a tension from the standard model due, for example, to composite Higgs, and we would not have found it in direct searches, showing again the importance of indirect probes of new physics at the LHC. It is the only remark I want to make that, of course, this is not standard model measurements. In the standard model, the couplings of the Higgs are predicted, and there is no progress you make on measuring input parameters of the standard model when you probe the Higgs couplings. And so this is about searching for new physics, even though you may like to phrase this in terms of some modifiers, parameters that modify indeed the standard model Lagrangian. It's a search for a Lagrangian which is not the standard model one. It is time to expand the box, including all the rest, and this is, and some items about on this line are the main topic of this talk. So, what is new physics? New physics can be many things, but if it is heavy, then it's equivalent. Searching for new physics is equivalent to searching for effective field theory, and the assumption that new physics is heavy is partially justified, but it may be relaxed at some stage. What is important is that if we make, for the moment, this assumption, we can systematically classify what are the possible effects that may emerge beyond the standard model, and so we end up with the tool by which we can be sure of not losing anything, and we can be sure that we explore in a useful manner what is new physics, if any, accessible through the. Also, we have to take into account that at a collider like the LHC, there is an interplay between two different regimes in which you can probe this same effective field theory Lagrangian. So there is the low energy regime in which you measure quantities at the electroweak scale, for example the Higgs couplings, the Higgs signal strength or branching ratio, and you ask yourself how this would change if there was an EFT operator. This operator would have a coefficient which I call 1 over lambda square. This lambda is not necessarily directly associated with the mass of a new particle. 1 over lambda square is essentially the Fermi coupling that corresponds to this D equals 6 operator. The corrections are of order, of course, of the bidimensional analysis of the electroweak scale square divided by lambda square. And so the only way to make progress in this regime is to measure as precisely as possible, reducing this one as small as possible, because if you want, the signal is not going to grow whatever you do. This is the reason also why, and this is something that is that will reach at some point an end at the LHC because of systematic uncertainties. At the LHC there is a precision program, but of course it cannot do measurements which are, say, per mil level in most of the places, right? Unlike, for example, what LEP could do. So, for example, if you ask me, let's study the Z pole properties at the LHC, there's probably not much to learn because LEP did it already with per mil accuracy that here we cannot reach. And also the Higgs couplings, with exceptions, we will have to fight quite a lot in order to improve exploiting, for example, the high luminosity LHC run. We should start at some point fighting with systematics. The benefit, of course, of the other manifestation that this effective field theory can have is that you can overcome, you can systematically overcome the systematics uncertainty if you, rather than probing, say, 100 GeV scale processes, you start probing energies, let's say scattering processes that emerge at an energy scale of the TV size, for example. Because the effects can overcome systematic, because this kind of probe receives a big boost with the collider energy, and so if you compare what was done at round 1, you easily discover that everything will have to be redone at 13 TeV with dramatically different performances, because in the TeV range the particle luminosities grow by an order of magnitude, so cross-section grows enormously, and furthermore you are allowed, to populate higher and higher energy tails of the distribution where these effects are even bigger and bigger. And so this is something that also easily improves with luminosity, because if you have enough energy to go here, then you will be dominated by systematics. You will have a bigger effect, but you will still have small statistics, and so increasing the luminosities you will keep winning. And so this is a nice way in which you can also try to make progresses not only at run 2 and 3, but also in the projection of the high luminosity LHC. This is a set of places where essentially there is some sort of free lunch in the sense that you can improve just by accumulating more data, of course, with the square root of the luminosity as unavoidable by statistics. So this is what I like to call the energy and accuracy frontier, which is the fact that if you are able to identify a process which you can measure reasonably well, in which your new physics is contributing in this way, and it's not completely obvious that you can do that, right? It depends whether there is interference between BSM contribution and standard model. It depends on the overall size of the standard model contribution. It depends on a number of things. But if you manage to go in this situation, then you can exploit these highly energetic measurements, okay? So trying to be as accurate as possible at energies which are as high as possible, and you can hope to make substantial progresses with not too much effort. So if we want to set a benchmark of what is an interesting measurement in this respect, we can think to LEP, where you could measure some kind of processes, in particular eminently neutral currents, processes at the 1 per mil level, at an energy around the z-pole or so, which is around 100 GeV. And suppose that there is the very same new physics effect that just didn't show up at LEP because it was right at the threshold that we want to probe in exactly the same channel, neutral currents. But now we go at the LHC and we can reach 1 TeV center of mass energy relatively easy, and I will argue that we can reach much better than 10% precision in this kind of measurements. And so if you have this, you see that if you have the same effect at 100 GeV that was 1 per mil, now it becomes 10% at 1 TeV. So if you are more energetic than this or more accurate than that, then hadron colliders win, even in processes well measured by LEP, which is not all what we need about, all what we care about. Of course, we can, I will show you an example in which there is a dramatic improvement with respect to LEP, but also we should remember that, I mean, there are many more processes, of course, we have access to at the LHC than at LEP. So we can do a much more complete exploration, and I will show you another couple of examples. Okay, so the simplest example is the simplest new physics you can imagine, which is oblique corrections, which you can attribute to 4 dimension 6 operators, which are typically called ST, or this with the hat European way, W and Y are these 4 parameters. All of them have been probed at LEP, at the Higgs pole, and not only at the Higgs pole, with per mil accuracy, and they are bound, okay, at the per mil level. Some of those are completely, I mean, for some of those there is nothing the LHC can do, because you see that S and T just modify the residues of the propagators, of the pole propagators, sorry. And so the only way to be sensitive to those will be to do better than per mil measurements of inclusive, for example, Z or W boson cross-section, which of course you cannot do. However, if you look at W and Y, they induce constant terms in the propagator, which means that respect to the Q square, so they are quadratically enhanced with energy. So are one of these examples of growing with energy effects that you can see if you measure neutral or charged Drellian at the LHC. This is a very simple experimental channel, of course, but still you need the experiments to fulfill a certain number of requirements, and not only the experiments for this to work. You need still an accurate experimental measurement, and if you look, already round 1 was capable to measure at 10% at the 1 TeV range. And so one would say that the reach of the data that we already have now are comparable with LEP. And also, if you look at the systematic component of the error, you see that it's pretty small, okay? This region is dominated by statistics. And as I told you, when I go to run 2, the statistics will basically become, will grow by more than orders of magnitude. And also we will collect a lot of luminosity. So essentially in this region, the error will go down to this systematic floor of around 2%. And furthermore, we will populate higher and higher bins. So assuming that the systematics more or less does not grow so much, we can keep extrapolating this column, if you want, and reach the conclusion, as I will show you in a second, that run 2 can surpass LEP in probing these 2 particular oblique parameters. This requires, of course, also theory errors well under control, and this is where the progress in PDF determination is playing a role, first of all. Also, the progress in the photon PDF determination is going to play a role, and of course, also QCD and electroweak calculation at higher order. But this is a very simple process, so all these things are clearly available. So the result essentially confirmed what I was saying. This is from the neutral Drellian channel, which actually should be supplemented by a tiny vertical line here, which corresponds to charged Drellian. And if you had to combine these two, you would already obtain a sort of ellipse like verticalish like this, which is already comparable or even better than LEP, which is this gray thing here. And if you zoom, okay, and because you want to go to run 2, then you see that LEP becomes a big inaccurate thing, and here you have so in vertical lines which are charged Drellian, leptoneutrino, and these potatoes here are the neutral Drellian, and if you combine them, you will find something like here, which is much better than LEP. And also you see that the progress keeps going. Okay, if you increase the luminosity, I mean in the way it should with the square root. Okay, so there can be a concern in the fact that you are probing the effective field theory at high energy, because we all know that an effective field theory is a low energy description. Notice that we did this already when we discovered Fermi scattering currents. These were seen only when the energy was close enough to the electroweak scale in order for this effect from the Fermi theory to show up. So it's not something particularly new, but still we have to be careful. In particular, we have to make sure that we are not exploiting this growth of energy too much. Okay, because ideally, if I go to extremely high energy, I can get an effect which is very, very big, maybe even orders of magnitude bigger than the standard model. And so it's true that I'm setting a limit, but I'm setting a limit on an effect which is extremely big, and maybe is not within the prediction of the effective field theory. So the effective field theory, or the underlying theory which is behind this effective field theory, does not really predict that effect. And so your limit will simply be inconsistent. And this is essentially what happens, for example, for the anomalous linear gauge coupling run one results. And so this plot is made in order to show this. So you have that. So the effective field theory is gonna finish its validity at a certain cutoff scale, which I call lambda cut here. So whatever energy is below this scale is well predicted by the effective field theory. So if I use in my analysis only data which are below this cutoff scale, can be 2 TeV, 1 TeV, I keep it varying here, I get a limit which, as you see, deteriorates, right? It becomes weaker with respect to the one that I have if I use the whole spectrum. However, I get a limit which is robust because I'm only using events which are where the effective field theory, by definition, okay, works. And so from this plot, I can learn a couple of things. I can learn that the strongest part of my bound comes from around 2 or 3 TeV. I also can compare the size of the bound with the mass scale, which is the cutoff of the effective field theory that I will get at this level of the W parameter of the Wilson coefficient in a particular model, okay, which is here, and it corresponds to around 10 or 15 TeV, which means that, well, I'm probing 3 TeV scale, a 15 TeV new physics, which means that I'm safe from that viewpoint. And I can also draw in this plane what are the predictions on the relation between the cutoff scale, that is the mass of the new state, and the Wilson coefficient of the new operator. I could draw lines, right, that correspond to different kind of scenarios. And for example, I can draw this line that corresponds to, say, the frontier between uninteresting models, okay, which is here, and interesting ones. So if my line here had fall inside this derivative expansion breakdown region, I would have concluded that my bound is not relevant. Instead, I can conclude that it's relevant. I can also verify with explicit models the correctness and also the impact that these things happen to have. For example, W compositeness like scenarios, or strongly interactive like this with the small G star are bound here. I mean, the reach here is superior to anything else, including direct searches. Okay, so the natural extension is to do die boson production. It is natural because these effects W and Y can be suppressed very easily if I do a composite X model with an intrinsic G star coupling which is a bit larger than G weak. Then even if M star, the new particle scale, remains low, this effect does not grow. It remains small, and so I can hide this effect. These operators that, the next value of operators I care about is instead these ones, which do not experience any of these suppressions. So at least in this scenario, they are just linked to the new physics scale. And they induce growing with energy effects, not in the Drellian process, unfortunately, but in this kind of vector bosons and boson plus Higgs production. Which essentially, well, skipping details, well, here only what you have to keep into account that given that this is an high energy probe, it is essential to remember that at high energy, the Higgs and the longitudinally polarized vector bosons, which are those where these operators do actually give a growth with the energy, are all related with each other by the equivalence theorem. They are related by the standard model symmetry, and so you cannot study one in isolation from the others. You have to interpret all of them together, and the number of parameters which you need to probe this, to study these things at high energy is 4, and you see it actually corresponds very easily to 4 operators in the long list of Borsov bases, which I think is this one. Okay. Then, of course, you can also translate, using the effective field theory, these kind of measurements at high energy into low energy measurements, or into low energy parameters, like, for example, this delta G1Z and delta kappa gamma, which are the famous anomalous linear gauge couplings that have been measured instead with, some accuracy at lab. You can also, well, we made some sort of phenomenological study. Well, essentially the message here is that all these channels are interesting, and the challenge that you have in these different channels is the fact that you have a background from the production of transverse vector bosons, okay, in the channels like WW and WZ, while in the channels with the Higgs you don't have this problem, but you need to use a boosted Higgs. And for the moment, until recently, nobody had hoped or believed or even wrote a single paper trying to do precision with boosted Higgs, but maybe this is even possible. Okay, so what can we say about the power of this approach? So if we stick to oblique theories, okay, so let's say universal, more precisely universal theories, then we also impose, you see, the fact that well, these W and Y parameters will be determined very precisely by what I told you before about Drellian. So let's just put them to 0. Then we end up with a nice plane in which we can draw the LAP linear gauge coupling limit, which is, known to be not particularly good because LAP didn't have much cross-section into the bosons. And we can overlay, you see, what we can do, which is a vertical line, because this particular channel that we studied, I forgot to mention, is only leptonic WZ, because this is where we found that it's easier to imagine you have a precise experimental measurement, and also where it is easier to suppress, at least according to our comprehension, to suppress the transverse background. So we studied this one, and we got this or this line, depending if you are, of course, at the LHC or at high luminosity LHC. If you want to cut this plane in other direction, you have to do some others of these channels, and HZ is one promising direction. This is the direction that will be constrained if you do HZ, if you study boosted X plus probably plus leptonic Z along this direction, as this gentleman did quite recently, and they claim that that it's actually possible to lift this degeneracy, this complete degeneracy, into something like this green region, which you see shrinks significantly now, LAP in all directions. Okay, this is very interesting. On this other side, you want to be more, if you want, more oriented towards some specific DSM scenario, the composite X we all like and love. Here we can parameterize essentially. Here there are several effects: loop suppression of certain operators, power counting. When you go at large star, you eliminate W and Y, as already mentioned, and other things. In the end, you can conclude that there are only 2 parameters that control these kind of things, but they go together with the S parameter. You see, so here, in this particular case, the comparison can be done also directly with the constraint from the S parameter, and you see that the bands are essentially comparable in magnitude, and also the S parameter. Well, you see, depending on what you do with T, the bound can be different. So you see that you are getting the picture, which is complementary to this other one, and nothing. And the S parameter was, is one of the most sensitive probe of its compositeness, as we know very well, together with X couplings. And so the fact that we can do something at the LHC is remarkable. Right. So once again, the most important plot in which I show how the limit on this parameter changes as a function of the maximal energy of the events that I put inside my fit. Okay. So first of all, okay. So these are our results. Okay, for high luminosity or for LHC. And here now I'm overlaying class of BSM theories. Okay, that give different prediction for the relation between the cutoff of the effective field theory, so really the maximal energy at which I can trust my effective field theory, so the maximal energy of the events that I have to use in my effective field theory to say something meaningful. And I see that here there is theories in which the quarks and the Higgs are both strongly coupled, which of course is something that we expect not to be at all realized in nature for several reasons. Here you have a line where the quarks at least are weakly coupled, so they talk to the rest of the world by G weak, but the Higgs is strongly coupled. And this is if you want, a W compositeness scenario, remedios, whatever you want. And you see that, for example, in this viewpoint, the LHC round 1 data, can constrain only these two kind, can probe only these two kind of theories. So it is true that, so there is an improvement with respect to LEP, which is the famous thing that LHC round 1 is better than LEP in anomalous linear gauge coupling, but it's also true that this success is completely, is relevant only for this kind of BSM scenarios, while we will arguably be more interesting into this line, which is weakly coupled quarks and weakly coupled gauge, which you see we can comfortably sit below this line, only provided that the measurements, that what we are doing is really a measurement, is not a bump hunt in which we search for an excess in the last bin of the distribution. Okay, this would mean that we are pushing too much the validity of the effective field theory. We are up to too big effects which do not exist in this theory, and so we cannot rely on them to probe this theory. Okay, so this shows the importance of precision in this business. Okay, so I had a number of other slides, but so this is just to tell you that even if you specify one specific model on which you can, on the same plane, put direct searches, Higgs coupling modification, and what we are doing, which is these vertical lines, there are non-fine-tuned, so large region of the parameter space in which there is a space of the other parameters, right, of this order 1 parameters that you can always have, in which this is the best probe that you can have. And, well, nothing, I have some slide about the transverse case, which is of some interest, but I will skip them. In particular, the interest here is in the fact that you can discover that there is a number of angular distribution that may improve your limits significantly, and is not yet understood how and to what extent you can take them into account. Maybe using neural network will help, but let me go to the conclusions. So literally, the LHC can do electroweak precision test, and the best way to do so is by energetic and accurate measurements. These two specific LEP parameters will be measured much better on LEP than LEP at the LHC, and will have an impact on some hypothetical BSM scenarios. And in this context, dye boson plays a major role, and especially now it will be true by a search strategy, which, however, needs not to be the search for just in the high tail of the distribution, must really be the measurement of the distributions, in particular the PTZ distribution, for example, in WZ. If you really do so, then you can really beat LEP, not with today's data, but with tomorrow's ones. And I think we can do more, and I think this is interesting. And also, I would like to say that for example, we heard this very beautiful talk about precision, and I think it's very important that the experimental viewpoint, and the experiments are doing fantastic things. Our colleagues from QCD are doing fantastic things, and it's very nice if all this work ends up into something that we can understand what is going on, we can give a BSM interpretation of, and maybe we can also suggest, as we are doing, different channels, different final state, different measurements that have to be done. And so these boson channels will also be studied to constrain all these 4 parameters I discussed about, and there is space also to do more delicate and complicated things related with the many peculiarity that this diboson signal has, decay angles and related stuff that up to now have not been addressed enough. Thank you.
We have time maybe for one question, or you're the only one with the...
Okay. This is a very interesting lecture that you gave, but I'd like to express the conclusion in a different way, which I think probably should be said. So the standard model is the standard model, and if you find the deviation from the standard model, that's incredibly interesting. And so in the regimes that you're talking about, where you're looking at general fits to high S-hat subprocesses in LHC events, one definitely has a lot of sensitivity to see that the standard model is violated. However, as soon as you see that the standard model is not violated and try and put bounds on parameters, as you explained in this talk, it gets very subjective.
No.
So could you
Subjective, I disagree.
Could you go back to the Banerjee Angler et al. Slide?
Look, which one?
Please excuse me. Could
Which
you
one?
go back to the Banerjee et al. Slide?
Sorry, which one?
Banerjee, Angler.
You tell me when to stop.
That one. No, it's
This one?
the one with the blue swirl.
This one.
The next one. Yes. So this is a very interesting paper that I frankly totally disagree with, and I've told the authors that. What they do here is they look at high transverse momentum Higgs production. And normally, I don't know normally, I mean, there's a perspective that says that's generated by an anomaly in the Higgs EZ vertex. But what these people say is we're going to totally ignore that operator. We won't even put it in the fit. We're going to look at some other operators on which this cross-section depends with an S over MZ squared dependence, and we put bounds on those operators.
Right.
Well, you can do it any way you want, but it's very subjective.
Subjective what? Sorry. There is only this effect that you can have that grows with the energy. So if you do your complete effective field theory fit,
yes,
right, you will find this, which grows with E square or M square, which is a factor of 100 or whatever it is, and then you will find your other effects.
Right.
Okay. Now you are asking why the other effects are not 100 times bigger than those ones that are here.
In particular, direct things that couple to the Higgs could be much larger than the operators you're testing here.
No, you're talking about direct production of other particles?
No, direct
Direct?
radiative corrections that directly affect the Higgs can be larger than radiative corrections that are basically precision electroweak corrections, which is what
No, sorry, these are direct effects that affect Higgs.
Well, all I'm saying is that it's subjective. Unless you can do some complete basis, you're making subjective choices. Similarly, you've stressed that where you cut off in S hat is subjective. So I guess what I'm saying is...
No, what I'm saying is wrong. So where you cut off in... Sorry. What I'm saying is that you should present and remember that the result depends on where you cut off.
Absolutely.
So once you have done this, there is no subjectiveness. It's just a question whether is my theory reliable at 1 TV or it is not.
Where you cut off is subjective.
No, where you cut off is an axis, so it's not subjective. So this, 2 is one subjective, one is another subjective. Okay? This presents the full information.
Whatever. I think I made my point, so I'll stop.
I think that makes for a good discussion at lunchtime. Thank you, Andrea, again, for this nice overview. So you have can change slides.
Okay.
And the last talk before lunch is by Brian Battelle on the status of BSM at the LHC.
Okay, well, first let me start by thanking the organizers. That's actually my first time to visit GGI and first time to visit Florence, so it's really a pleasure. So I'll try to make this relatively quick so we can get to lunch. So I was charged with talking about the status of BSM explicitly not discussing electroweak symmetry breaking, so I'll try to stick to this charge. With that in mind, let's start. So the one very important thing that we learned was that the supersymmetry bet was settled. Okay, so this bet was made some time ago, and it was settled with cognac. So science is working. We're reaching consensus. So certain types of supersymmetry are ruled out, but not all types of supersymmetry. Okay, so why BSM? So we all have this laundry list of things, hints that suggest us to go beyond the standard model. And so the real question is, where should we look? I don't think you can really make any more a very robust argument, or airtight argument anyway, where you should look. You should just basically look anywhere you can, and that means wherever you have an experiment. And so for this talk, obviously we're going to be mostly interested in the LHC. And along with my charge, I'll mostly be thinking about these questions. So the questions of dark matter, neutrino masses, and the matter-antimatter asymmetry. And even within these topics, of course, there's a wide range of scales, different types of models that could explain, not necessarily at all clear that the LHC is the right tool for this. But there are certain classes of scenarios where the LHC is interesting. Okay, so let's start with dark matter. Okay, so obviously one of the main motivations to think about the new physics at the LHC in terms of dark matter is the Wimp paradigm. And so this paradigm of dark matter in kinetic equilibrium and chemical equilibrium freezing out suggests a scale of around a TeV if this coupling is sort of weakish strength. And there's lots of different realizations that this could take. So one simple realization is just the case of electroweak dark matter. So this is just the case of a Higgsino or the Wino in supersymmetry or minimal dark matter with higher multiplets. And so in this simple scenario, dark matter annihilates to weak gauge bosons, and the right relic abundance is achieved for 1 TeV Higgsino, 3 TeV Wino. And indirect probes, particularly the gamma rays, are placing relevant constraints on thermal Winos and starting to say some interesting things about Higgsinos. On the other hand, direct detection is essentially very difficult with these states. So scattering proceeds at the loop level, and there are some accidental cancellations. So the cross sections may even be below the neutrino floor. And relevant for colliders is this sort of irreducible radiative mass splitting, so in the range of 100 to 300 MeV. And so this renders charginos long-lived, at least on collider scales, and their visible decay products are soft. And so this leads to the idea of the disappearing track search. We already heard about this in the talk, so I don't have to spend much time on it. But just to sort of give the status, so the idea again is you produce, say, a chargino, and it travels some distance and leaves some tracks in the inner detector, and then it decays, and the charged particle that it decays to is soft, and so it's a disappearing track. And so the notable thing now is that the LHC is pushing now beyond the LEP limits for pure Higgsino. So now the limit essentially is in around 150 GeV, and the limits are somewhat stronger for Winos. Okay, so in the 400 to 500 GeV range. Now, looking ahead, this is going to these sort of benchmarks are going to remain challenging at the LHC. So here's a recent study by some of my colleagues at Pittsburgh, and basically what it shows is that the LHC will not be able to quite probe, even with 14 TeV, 3 inverse Adelbarn, it will not be able to probe sort of a thermal Higgsino, which is around 1 TeV. A future 100 TeV machine might be able to do better, but it seems that some new ideas are needed. So a couple of interesting ideas that were discussed recently were perhaps going to track-based analyses. And essentially the idea is to try to get as most out of the particles which have a large boost. And so rather than cut hard on, say, PT, you can look for tracks with high momentum. And in particular, you could even consider for example, for a future collider, sort of a forward tracker component. The particles with the largest boost tend to go in the forward direction. Another idea is to consider sort of a two-hit analysis. So the current Atlas analysis is based on 3 pixel hits, and this group was considering, for example, 2 hits. And as I understand, there's some discussion within Atlas about whether this is feasible. Okay, so new ideas are needed to probe this interesting benchmark. Now, if we go beyond electroikinos, beyond Higgsino and Wino to more general neutralinos, there's a lot of interesting possibilities that open up in terms of collider signatures. So you could have 2 leptons plus MET, 3 trileptons, 4 leptons, and so on. And so the current constraints from Atlas and CMS are starting to push the constraints up to sort of in the 500 to 600 GeV range, depending on which signature you're thinking about, for the heavy Chargino neutralino state. And this can provide some complementary probes to other handles, such as direct detection and indirect detection. This is a study from CMS on their high luminosity reach, and this is discovery reach, so when you compare to this, it might not look quite so impressive, but remember that this is, let's see, this is 5 sigma discovery reach, and so this can go almost up to 1 TeV in this heavy Eno mass. And so sort of a complete picture might emerge at some point in the future. So this is one way to sort of think of the simple neutralino system. You have, if you decouple all the other particles, you could think of just having a sort of 4 parameters. So if you fix tangent beta, then you can think of the relic density as being a surface. And so here is a picture of that surface. And so X, Y, and Z axes are the different mass parameters. And depending on where you're sitting, the neutralino might be a Wino or a Higgsino or some mixture. And sort of the upshot of this study was that at a future 100 TeV collider with a combination of certain searches, certain direct searches, and direct detection, and also indirect detection, one can probe most of this neutralino surface. Now, we can also think about dark matter from a more bottom-up perspective, and so roughly I would say 10 years ago, this started to be pushed. So the idea is you just think about, just suppose dark matter couples to quarks or gluons through some effective operator. Then you could think of a signature, which is the monojet signature. And so this gained a lot of traction and led to a host of different mono X signatures. So this was a really good development, something you might not have thought about just thinking in terms of supersymmetric dark matter. And then there's been a progression, so various concerns regarding the validity of the effective field theory and so on have prompted people to try to UV complete or partially UV complete these simplified models. And the interesting thing about that is that leads to, when you have the mediator in the game, it leads to different kinematics that suggests you might adjust your search strategies, and there's also new signals associated with these mediators. And so now, finally, the progression is that people are trying to UV complete these simplified models. For example, if you have an anomalous gauge boson, which is your mediator, then you might want to add some fermions, and those can provide even additional signatures. Okay, but often these are still distinct from supersymmetric dark matter. So I think the interesting thing about this is that sort of the desire to interpret in a consistent way some of these analyses have actually led to new signatures being proposed. So I think that's a healthy outcome. Okay, so monojet. This is a kind of a nice way to think about it. So this is a plot of the mediator, the Z prime, and the dark matter. And so in this regime, when the mediator is heavy, in comparison to twice the dark matter mass, the mediator might typically decay into dark matter. This is where you would have your monojet signature in this range of parameter space. In this range of parameter space, you would have your dijet signature where the mediator can't decay to dark matter. And so by now there are various searches. So this is a recent search by Atlas, and they're probing mediator masses up to 2 TeV. And you can try to essentially exclude some part of the parameter space where you could get the right thermal relic abundance. And on the other hand, if the mediator is light in comparison to dark matter, you can have a dijet signature over this broad range. Okay, so I'm not sure what the ultimate conclusion of this would be, but perhaps a good goal would be to sort of try to completely characterize, where a thermal relic can exist, and see to what extent you can test that hypothesis. And just stepping back a little bit more broadly, if we take this thermal relic motivation seriously, it turns out actually that you don't have to stick around the weak scale. You can actually go much lighter. You could potentially go down to the MeV scale in terms of your dark matter mass. And in that case, you also need a light mediator to get efficient annihilation. And so there are various ways you can do that, but perhaps the simplest way is to think about these 3 renormalizable portal operators. So there's the Higgs portal where you couple a scalar to the Higgs mass term. There is the vector portal where you couple a new U1 to the hypercharge. And then there's the neutrino portal where you couple the right-handed neutrino to the LH operator. And then these different mediators could also talk to dark matter. And there's a huge effort trying to now probe these sort of scenarios. And we saw one example also in one of the talks this morning. So this is the LHC B search for dark photons. And so anytime you have a photon, you can think of mixing into a dark photon, and then it could decay back to leptons or other charged particles through the same interaction. And there are proposals for prompt searches and also displaced searches. And so this is an exciting way to use the LHC to probe light dark sectors. Now, we can go beyond that, and there's a whole host of experiments that I don't have time to discuss, but I'll just mention one thing that I've been involved in. So you can also use fixed target experiments or beam dump experiments. So this is an example with the Miniboon experiment. Miniboon, of course, is a neutrino experiment. But in the basic setup, you have a proton beam that can collide with, say, a beam dump, and it could produce dark matter out of those collisions. And then it could scatter with nucleons or electrons in the detector, and then you can look for those recoil signatures. And after some long period of time, there finally have been some searches coming out with from a dedicated run. And so one, for example, you could produce dark matter in the decays of mesons, and then it could scatter through exchange of a dark photon. And so this blue line shows the limits from the first search, and it covers some new parameter space. And there's actually a variety of new proposals for fixed target experiments that can be carried out to test these light dark sectors. Okay, I don't have time to discuss it, but just to give you sort of a picture, this is the whole range of experiments and dark matter masses, different types of dark matter candidates. There's going to be actually quite a few talks at this meeting, so I'll refer you to those. And you can also look at the recent Cosmic Vision study for a big overview. Okay, let me switch gears. So another strong motivation for new physics at the weak scale would be the scenario of electric baryogenesis. So the basic picture is just shown here. So you have the idea is you have a strong first order electric phase transition that proceeds via bubble nucleation. And if the Higgs has new CP violating interactions, then scatterings with the bubble wall can create a net baryon excess. And this will bias this Faileron creation of a net baryon excess in front of the wall. And then as the bubble expands, the baryon excess will be incorporated into the regions with broken phase. So I'm just going to focus for this talk on the first order phase transition part, and we'll have a talk in this meeting by Geraldine Servant, who will likely give a broader overview. But the key thing is that we have new physics that couples to the Higgs, which can modify various interactions, in particular the potential interactions, and there can be a complementary probe from a sort of a stochastic gravitational wave background signature. Okay, so how can we actually generate these corrections to the potential? So one possibility is new colored or charged bosons. So you could imagine a toy model where you have some new colored particle or new charged particle coupling to the Higgs. And this can give a sizable contribution to the thermal potential if the boson is light, say below a couple hundred GeV. And in this case, Higgs coupling measurements are already providing a very important probe, very stringent probe in some cases. And it's kind of hard to see, but this is a couple of plots taken from this paper. And essentially, the black lines here are where you would like to live if you want a strong first order phase transition. And you can see here that this is the case of a color sextet particle, and you're getting very large corrections to the Higgs to glue coupling. So this scenario essentially would be ruled out. Other scenarios, for example, sort of a toy model for a right-handed Stow, just electrically charged, hypercharged particle, generate rather small corrections and still could be allowed. So really to decisively test this scenario, you need to measure the Higgs coupling very precisely. And this would probably require a future collider to do so. Now, of course, you can also look directly for these states. Although the decays are somewhat model dependent, so making a very firm statement might be difficult, but that's another possibility. So these scenarios already are under some tension, but still might be viable. Now, another possibility is just to try to modify the potential at the tree level. And so maybe the simplest scenario is just to add a phi to the 6th operator. And so this was studied, and here's a plot showing, for example, where you would get a strong first order phase transition as a function of this cutoff scale, suppressing the higher dimension operator. So you need a very low cutoff scale of order TeV or so. And an interesting consequence of these type of scenarios is you get a shift in the Higgs self-coupling. So here again in the same plane, so if I look at 125, I'm getting coupling shifts which are positive and can be order 0.5 to 1 or so. Now if I look, actually, the shift is positive and typically turns out to be positive. And we can see here that that actually makes it more difficult to see or detect the triple Higgs coupling, and that's because the interference in double Higgs production becomes stronger, and so this becomes actually more difficult. Now you could try to UV complete that sort of scenario where you have this phi to the 6th operator, and one scenario that is often explored is a scalar singlet. So this leads to, again, modifications to triple Higgs couplings, also modifications to the Higgs ZZ coupling. and also potentially some complementarity with gravitational wave signatures, and this has been explored in this recent paper. So this plot shows all of these dots. Basically, you're getting first order phase transition. In the blue dots, you're also getting a strong first order phase transition. And in the green dots, you have potentially observable gravitational wave signatures. And it shows it in the plane of the shift of the coupling, of the triple Higgs coupling and the Higgs to ZZ coupling. So, for example, with a future ILC 500 machine, you could really start to probe a lot of these parameter spaces, a lot of this parameter space through the shift in the triple Higgs coupling and the Higgs to ZZ coupling. Okay, so the final thing I want to touch on is neutrino masses. So there's many models for neutrino mass, probably as many models as there are for dark matter. So you could have tree level generation of a sort of lepton number violating mass term, or you could generate this at loop level. And obviously we can't explore all of these. One thing to note though is in many of these you'll have new additional states, new charge states that you can search for with LHC and other high energy colliders. I'm going to talk just really focusing on the type 1 Seesaw scenario. Okay, so this is the basic schematic for the type 1 Seesaw scenario. Hopefully most of you are familiar with it. But basically you generate a small neutrino mass through this suppression. You can think of this as some propagator suppression in this Feynman diagram. So in terms of LHC, we could ask, well, is there any reason we might expect the Majorana mass near the weak scale? In principle, it could lie anywhere down all the way down from the EV scale up to sort of close to the gut scale, and still you could generate the right neutrino mass. So a few things I can think about that might point to the weak scale. So one would be a couple of different scenarios of leptogenesis, either resonant leptogenesis or ARS leptogenesis, or leptogenesis through oscillations. Possibly there could be some connection with the hierarchy problem. Very generically, you might expect new physics there. There have also been proposals where maybe the right-handed neutrinos could serve as the top partners, sort of in the neutral naturalness paradigm. Or you could have the right-handed neutrinos sort of serving as a mediator to thermal dark matter, and that would also maybe point you towards the weak scale. So there might be some story that you could think about telling that would connect these two, but generically, the right-handed neutrino mass could be anywhere in this range. Okay, so if we just go ahead and push forth, and we imagine that the Majorana masses are near the weak scale, then there are various different signatures we could look for. So we could just produce the right-handed neutrino through Drell-Yan, and then we could look for trilepton signatures, or also dileptons plus jets. And so these have been searched for. A way to characterize or interpret this is in the plane of the mixing angle squared. Okay, so the mixing angle is basically how much you're mixing between the ordinary, the left-handed neutrino and the right-handed neutrino, and that controls the production rate and also the lifetime. So if I plot that versus the right-handed neutrino mass, I'm starting to probe some interesting region of parameter space here. So down even to mixing angles of order 10 to the minus 5 mixing angle squared. Now, once you go to lower masses for the right-handed neutrino, it turns out that they become long-lived, and that's just because you have to decay through an off-shell gauge boson. And so you have a 3-body phase space. You also have a small mixing angle to pay. So it's very natural for these things to be long-lived in this region. And so that leads us to, how could we actually search for those? And there's been a lot of proposals recently to try to think about how to detect long-lived particles. So there's various different proposals. There's the Methuselah detector, there's Codex B, there's the phaser experiment and others. There's also other experiments not directly related to LHC, like NA62, SHIP, Bell 2, which will also have something to say about these long-lived particles. So if I put everything together, here's sort of a plot of the mixing angle squared versus the right-handed neutrino mass. And you can see here at high masses, this is where the LHC is in the game. At low masses, this is where some of these other sort of long-lived particle searches might have a role to play. So just to compare, this is a recent plot from the Methuselah white paper that studied the physics case for this new detector. And you can see Methuselah is sort of competitive and even in some ranges better than SHIP, depending on the precise mass. And then this is just to sort of guide where this recent LHC search would compare. So it starts to cut into this region. So one thing I want to just emphasize is it's really very difficult in this mass range to get down to the very naive seesaw line. And that makes sense, I think, it's just because you expect a very small Yukawa. It's not to say that you could not get the correct neutrino mass in this region. There are scenarios like inverse seesaw where you can easily do that, but just this very naive implementation of the seesaw is of course difficult to test. Okay, so I'll just wrap up. So I told you about the status of some classes of models within dark matter, electric baryogenesis, and type 1 seesaw. And then let me just end by saying, obviously the LHC is approaching an important milestone with the completion of run 2. And we really should take this question to heart. Where do we go from here? This is our assignment in the workshop. So I personally actually don't have any excellent ideas. I'll just leave you sort of with some vague things that I think are generally true, but hopefully we can make some progress on that question. Thanks.
Other questions, comments? Yes?
So for the electroweak phase transition causing the gravitational wave, you showed a plot for the ELISA, right? Yeah. So here, do you consider the gravitational wave coming from the typical sources of turbulence, sound wave?
Yeah. I think all those sources are taken into account in this calculation.
Okay. But for the case of the bubble wall, so as the speed of the bubble wall collision increases, the gravitational wave energy density should increase, right? In one of the sources. On the other hand, for for the typical electroweak baryogenesis scenario, you need to keep that bubble wall speed below the sound wave speed. So can you do electroweak baryogenesis keeping that in mind and also cause the strong first order phase transition causing the
yeah, so I don't know the answer to the question. So in this paper, which is not my work, they only studied if you could get a strong first order phase transition. So they basically were trying to study the connection between Higgs couplings and potentially gravitational wave signature. So if there's any complementarity in that. They studied this model and several other models. So I personally don't know the answer to that question, but that wasn't investigated in this work.
Okay.
Yep.
Thanks.
Last question. So maybe let me ask you on slide 9, if I may. You were discussing the projection of LHC and then mentioned mentioned the fact that at forward tracker components for FCCHH you could go to eta 4, but actually we'll have this already at LHC, and the inner tracker will be extended in the forward region. So I was wondering if this was included in the projections there or not.
Well, yeah, this is a different study, but I think in this study they did not include any forward tracking for LHC. Mm-hmm. So this was only proposed sort of as a hypothetical detector component for FCC, but Yeah, so that's very interesting. I mean, I don't know if anyone is looking at that, but because the general point of one general point of this paper is that if you look at sort of the boost, the boost, which is controlling how far the Higgsino travels, versus eta, it tends to peak more in the forward region in comparison to where cuts are being performed in standard searches. So yeah, it would be very interesting to look into that. I don't know if anyone is doing that, but yeah.
Okay. So we can expect major improvement then at HLLHC from that exploiting that feature then. Okay. So I guess we are all hungry and we'll go for lunch. So let's thank the speaker again.